So welcome to the first flipped classroom video, and we're going to be trying this for Unit 3, which is our energy unit, which traditionally begins right after midterm week. And there's so many different things with energy, and it's around us at all times. The simplest definition we're going to use for energy is that energy is the ability to do work. And energy, and once we go through examples and we learn about the units, it'll make a lot more sense. But for now, I'm just going to tell you that it is a scalar quantity, meaning there's no direction associated with it. So it's the ability to do work. And when work is done on a system, the total energy of that system is changed. So the way that we're going to define work is it's the transfer of energy to an object when the object moves due to the application of a force. So when the object moves or is displaced, so due to the application of a force. So on your reference table, we're going to have work, which is capital W, equals force times distance. And like I said in the definition of energy, if work is done, it's also going to change the energy on the system. So we have delta of the total energy. So it's a change. And if we think about the units here, I'm going to leave it as work. Force has units of newtons, and displacement has units of meters. So work is going to have a unit of a newton times a meter. So a newton meter, or traditionally it's going to be called joules. So that's going to be the standard unit for energy, which is just going to be a J. And a joule, it's a derived unit, and 1 joule is equal to the amount of work done when 1 newton displaces an object 1 meter. And notice how mass isn't in this formula, so it's just something to consider. Okay, so here's our first sample problem. So we have a 2.3 kilogram block resting on a horizontal surface. A constant force of 5 newtons is applied to the block at an angle of 30 degrees to the horizontal, as shown in the diagram. So we want to determine the work done moving the block a distance of 2 meters. And if, let's say, this block is displaced 2 meters along the surface, we only care about the part or the component of the force that is in the direction of the displacement. So in this case, it's being displaced to the right. So I am only going to care about the x component of this force. So if I come over here and make a knowns and unknowns chart, well, I know the force 5 newtons. It's a 5. We know the mass. We know the displacement. We do know the angle. But I do not know the x component of the force or the work done. So first, I'm going to find that x component of the force. So I'm going to do Fx equals F times the cosine of theta. So Fx equals 5 newtons times the cosine of 30 degrees. Make sure you don't forget that little degree symbol, since that is a unit. When I multiply that out, I should get an x component of the force of 4.3 newtons. So I can go up to the diagram and I can label that. Okay. Once I have that, I'm ready to figure out the amount of work done. And like I did in the previous page of the definition, work is equal to the force times the displacement. So we have work equal to the force, which is going to be this 4.3 newtons, times the displacement, which is 2 meters. So to displace this block a distance of 2 meters along the x-axis by applying a force of 4.3 newtons, I did 8.6 joules of work. And it's a scalar quantity, so there's no direction associated with it. Okay, moving right along. So next page we have power, and work and power go hand in hand. So power is also going to be a scalar quantity just like work. And power has one of my favorite definitions in physics, and it's the rate at which work is done. So power, the rate at which work is done. When we think about the rate, we're thinking about the time. So power, capital P, is going to be equal to work over time. So the rate at which work is done. Now, it's very easy to remember this because if you want to have power in your lifetime, you need to work over time. So work over time, and you're going to have power. And it's just a very simple way to define it. If you take it a step further, we've just previously learned that work is equal to the force times the distance. So we could also use P equals FD over T. And we could take that a step further. And this distance over time, well, we know distance over time is equal to velocity. So it's also equal to force times velocity. So depending on what the problem gives you is what you are going to use to solve it. So a knowns and unknowns chart, as always, will be very helpful. Now when we're talking about units, well, here's our first formula. So we have work over time. We know the units of work are joules and time is seconds. So joule per second, or I'm sure you've seen this before, watts. So one joule per second is equal to 1 watt. Okay, let's move right along to the sample problem. So we have a 7.8 times 10 to the 2 man, that's his weight, does 8.58 times 10 to the 3 joules of work in 12.3 seconds by running up 3 flights of stairs to a landing vertically above his starting point. What power does the man develop during his run, and what is his vertical displacement? Okay, so first let's consider what we have, and it's going to be tough here. I didn't give myself enough room, but we know the weight, so I'm just going to put the weight as what we know. We also know the amount of work done. We know the time, which is 12.3. What we don't know is the power developed or the vertical displacement. So first, what we want to get is power. And like we said, power, if we want to have power, we got to work over time. Okay, the work is this 8.58 times 10 to the 3 joules. I like to put parentheses, especially when you're using scientific notation, over 12.3 seconds. And we'll divide that out. You should get 698 watts. And now we have one more part to do. We're looking for the vertical displacement. So we're going to do work equals force times displacement. Again, we were given the work done. We know the force is the weight of the man. It's the only force that the problem gives us. So I'm going to divide both sides by this 780, or 7.8 times 10 to the 2. And we should get a vertical displacement of 11 meters. Okay, and there's one more sample problem. You can try it on your own now, and we're going to go over it in the next class period.